Okay, thank you, Baruch. Okay, so thank you for sticking around. I'm going to talk about basically topological states in non-equilibrium driven systems. And I'll show you two types of systems that actually can exhibit topological pumping in this kind of far from equilibrium regime. So first, let me thank my collaborators, Erez, Mark, Gil, and Michael Levin, and also a student from Caltech, Paraj Titum, who did most of the numerics, at least in the first part of this talk. זה המחשב שלך. This is PowerPoint on your computer. Okay, so in non-equilibrium, we can basically ask what types of new topological systems can we get for periodically driven systems, and I couldn't have a better introduction than just to have Asa speak before me. Not that it was planned in any way, but let me still iterate. So, you know, in the Middle Ages, the alchemists tried to convert lead into gold by shining moon rays on lead, and you know, maybe in the 21st century we could do something like, you know, shine a laser on some kind of ordinary material and get something that's topological. So this is going to be the theme of this talk. So in terms of studying topology in time periodic Hamiltonians, so we could ask the question whether time periodic Hamiltonians, what is their topological classification? The problem with that general question is that in general, we don't have any eigenstate for general time dependence. We don't have any eigenstates to use for these classifications. But for periodically driven systems, as Asa already explained, we could basically use Floquet theory. And Floquet theory tells us a very simple thing. It tells us that basically what we could do is we could think about the unitary time evolution operator. Is there a pointer here? Okay. We could think about the unitary time evolution operator and decompose it into two parts. The first part would be a periodic unitary matrix, and the second part would be an exponential of a fixed matrix. And we could think about this as the Floquet operator, HF. And as Asa mentioned, the eigenvalues of this HF, they are called quasi-energies, and importantly, they lie in a circle, basically between 0 and 2 pi over t. Okay, so this is a periodic coordinate. And once we have this decomposition, we can basically now think about a possible strategy for doing a topological classification, and that is we could classify the topology of HF because HF is kind of a Hamiltonian. Okay, so it would have, say, it would depend on momenta, and we could study its edge states, etc. But I'm going to show you that actually this is not a full classification. So just studying the properties of HF is not sufficient. And actually, time-dependent systems can actually show a much richer behavior than time-independent systems. So again, if we have, this is still part of the introduction. So if we have Floquet block, if we have a lattice system which is periodically driven, we now have Floquet block bands where we have a quasi-momentum in how many ever dimensions that we are in, and then we also have our quasi-energy, which is a periodic coordinate. And then again, we could now think about looking at this band structure and thinking about its topological classification. Okay, so so far there have been several suggestions of basically systems where we could take a time-independent system which is almost topological like graphene, or just topologically trivial, and add some time-dependent perturbation, which would basically turn the system into a topological system. So for example, in graphene, you could basically get a band structure that looks like a quantum Hall state by shining circularly polarized light. Or in semiconductors with spin-orbit coupling, you could get a band structure of a topological insulator by shining above band gap radiation. Now, there has been also several experiments. Let me just mention them. There has been an experiment in the solid state, basically shining light on the surface of a topological insulator by the group of New Gedik. But there's also been experiments in cold atoms, basically basically realizing this kind of Haldane model by having a time-dependent system, or a system in a fully optical system, which also realizes the kind of Haldane model. Yeah, this actually should be 2 different papers. This is a wrong title. Okay, so now we could look at closed interacting driven systems. Okay, so far I've just talked about the band structures of these systems, but now we could think about what happens in the presence of interactions, and I want to make the following claim. If the system is interacting, but it's a closed system, so it's not connected to an external heat bath, at very long times, if the system is time dependent, I'm going to find the system in kind of an infinite temperature state. It's still if I start with a pure state, I'll still remain with a pure state, but this pure state will be so random that basically any correlation function that I'm going to measure will look as if I'm measuring this correlation function in an infinite temperature state. Okay? Now, we have to make a disclaimer here. We'll assume here that this statement will be correct. For example, we have to assume that there's no many-body localization or anything of that sort, so the system is ergodic. And if you want to understand why, you could just think about if these are the quasi-energy bands, and you think about some initial state where you say put fermions in this kind of band structure. You could, since we've discussed that the quasi-energy is only a periodic coordinate, it's only conserved mod omega, you could easily have situations where you have a scattering process which basically scatters, say, one particle inside this red band, but actually moves the particle from the red to the blue band and still conserves the total quasi-energy modulo omega. Okay, so these type of processes actually tend to increase the entropy of the system and yield this kind of infinite temperature state, which would be kind of completely random, at least in terms of the populations. Okay, so now we want to ask the question, can we actually find or see topological phenomena in systems which are interacting and externally driven? And what types of topological phenomena can we find? So actually, can we get this kind of topology change by adding a time dependent to a system, or are we going to end up always with a kind of a very hot and uninteresting state? So there's kind of 3 ways which you could imagine doing this. I mean, there could be more. This is 3 ways which we thought about proceeding. One of them is to consider disordered systems, and I'm going to show that in disorder-driven systems, there is an interesting phase which we call the anomalous Floquet-Anderson insulator, which is fully localized yet topological at the same time. Okay, so this will be one possible avenue, and this system could basically be non-ergodic yet topological at the same time. A different avenue was basically to consider quasi-steady state, so kind of intermediate time behavior between this kind of infinite temperature state and the initial state. We could have, for some intermediate time regime, we could have an interesting state which could actually exhibit the topology, and I'm going to talk about this in the second part of the talk. And the third possibility, which I'm not going to talk about, I'm just going to mention, is to consider coupling of the system to an external heat bath and try to see what kind of steady state arises once you do that. Okay, so let me again start with this anomalous Floquet-Anderson insulator. What is this anomalous Floquet-Anderson insulator? It's basically, again, as I said, it's a fully localized system. So it's a 2-dimensional system whose bulk states are fully localized. There's not a single state in the bulk which is actually extended across the system, but yet it does have chiral edge states, basically, that are going to lead to quantized non-adiabatic charge pumping, and I'm going to argue for that in a second. Okay, so again, I'll also explain in a second what's the difference between this and a regular quantum Hall state, which we know it could be disordered and have chiral edge states. So the idea, again, the special thing about this state is that the bulk states are fully localized, and that's not possible in a quantum Hall state. And to understand why this is possible, what we have to understand that basically these Floquet systems allow us to have kind of a richer configuration space than the static systems. The reason is basically simple. In static systems, the energy basically lies on a line, while, say, the momentum coordinate is periodic. So we are kind of we have states on this kind of cylinder. While in the Floquet systems, the quasi-energy is also periodic, so our kind of states, they can lie on a torus, on maybe a high-dimensional torus. So you could imagine that there's more topological configurations kind of for these Floquet systems than for these static systems. And this is exactly the case for this anomalous Floquet-Anderson insulator. So what happens here, what happens basically in time-dependent systems is the following. In these periodically driven systems, you could have a situation, so now considered even, it could be even a clean system, but you could have a situation where you have two-dimensional systems whose Chern numbers are all 0, yet it exhibits chiral edge states. Now, how is this possible? This is not a possible situation for a quantum Hall state. In a static system, for quantum Hall states in a static system, edge states are always accompanied by non-zero Chern numbers in the bulk. And here I claim that all the Chern numbers could be 0, yet I'll have topologically protected edge states. How is this possible? So what we have to remember is basically that the Chern number actually counts the number of edge states kind of above the band, minus the number of chiral edge states below the band. Now the point is that if you're for these Floquet systems where the quasi-energy is periodic, you see this state has this bulk band here has one edge state above it and one edge state below it. The Chern number is 0. And the same thing goes to this other two-dimensional band here. So both of these bulk bands have Chern number 0. Okay, but still the number of edge states below and above is 1. Okay, and there is no problem because the quasi-energy coordinate is periodic. Okay. You could ask also, what is the correct topological invariant? Clearly, the Chern number is not the full topological invariant characterizing these states. And there's a different topological invariant which actually takes into account the full time dependence of the system and is basically could be computed as a three-dimensional integral. I'll not go into that here. And you could also ask, okay, so maybe theoretically it's possible. What type of systems actually kind of exhibit this behavior? So we basically identified two types of models where you could have this phenomena. One of them is really kind of a situation of a very strong driving, and I'll talk more about this type of models in a second. But this is a situation where everything is time dependent. All the hopping parameters and all the on-site potentials are explicitly time dependent. You could also realize these type of systems in weakly driven band structures where you create a resonance between the valence and conduction band, but you use, say, a very uniform weak drive. Okay. But I'm going to focus on this kind of first type of models. And actually, I want to give you a very specific model that realizes this type of state. And this is the model. So the model is on a square lattice. Okay, it would be very easy to follow. So if you've been sleeping so far, and you could kind of wake up and try to follow me here. So we're on a square lattice, and we think about 2 atoms per unit cell. And we basically take our period of the drive and we divide it into 4 periods, into 4 sub-periods. In the first sub-period, we turn on this red bonds for a very specific time, and this is the time that basically moves one particle from the black to the white sites, or vice versa. And then in the second part of the second sum period, we turn on the hopping on these blue links, and the third part we turn on the hopping on the green links, and then those yellow links are turned on in the fourth part of the evolution. Okay, now if you follow what the particle would do, if you say started on this white side here, you could see just by following the evolution, the Hamiltonian I just gave you, that if you start a particle in the bulk, it will always kind of go around a square and return to its original position. And this doesn't depend whether it's on the white or on the black sides. But if you start a particle on the edge, on the white sides, you would see that it actually moves in each period, it actually moves 2 sides to the left. And if you start a particle on the black sides, on the bottom edge here, you'd see that in each period it moves 2 sides to the right. So you explicitly see in this model that there is a chiral edge state propagating on one edge and another chiral edge state propagating on the top edge. And you also see that the bulk is completely trivial in the sense that every particle just returns into its original position. And in fact, the bulk Floquet operator is just the identity. Okay? Every particle will just go back to its original position. Now, you could also add some sublattice potential to this model, and they basically split a single flat band into two bands, which is more like the picture I've showed you before. Okay, so there's two bands, their Chern number is 0, and you have a single chiral edge state on each of the edges. Okay, so now what is the relation to this order? Okay, so I want to remind you that in the quantum Hall case, if you have edge states, as we discussed, you also have to have Chern numbers. For example, this would be a situation with non-zero Chern numbers, and you'll have a single edge state in this gap over here. But if this is a quantum Hall system, if this is a band structure with non-zero Chern number, basically, I claim that this band structure cannot be fully localized. And it's a well-known argument. If you have a band structure with a non-zero Chern number, it necessarily have a Hall conductance which is proportional to the Chern number. Therefore, say if I put it on a cylinder and I pump in magnetic flux, I have to transfer charge from one edge to the other. And this is only possible if there are delocalized states in the bulk. So if the Hall conductivity is non-zero, the Chern number is non-zero, I cannot fully localize the bulk. I always have to have a delocalized state in the bulk. So the situation here is very different. We have 0 Chern numbers, okay, and we have this chiral edge state at the same time. So we could add this order. And we can imagine that if the Chern number is 0, 0, I could fully localize this band, this bulk bands here, but I can really not localize this edge state because it is chiral. Okay, so once I add this order to this type of band structure, I immediately get a fully localized bulk, and the edge state remains stable. Okay. Now, if you think about this, this is a very weird situation, because now let's think about what happens how do the states flow once I start pumping flux into a cylinder, in a cylinder which it has this phase, this AFAI phase, which is fully localized and has this chiral edge states. So if I start adding a flux, you know that once I add a full flux quantum, I'm going to see a spectral flow. And in fact, these chiral edge states, okay, the flow of this chiral edge state will be such that each chiral edge state will flow to the next chiral edge state with a larger momentum initially. Okay, so I'll have this kind of spectral flow that kind of moves the edge states up as I increase the number of flux quanta in the cylinder. Now, usually, if there's a delocalized state in the bulk, then this kind of spectral flow can stop in the delocalized band, okay? And then it could kind of emanate again from the delocalized band. So I could get a picture like this. But if all the bulk states are localized, then the bulk states cannot flow. A localized state cannot flow if I add flux in the cylinder. Its energy can only change exponentially. Therefore, once I add this order to this kind of system, I must have that the edge state kind of fully traverses the whole spectrum from top to bottom and winds around the momentum quasi-energy zone, basically from minus pi to pi without terminating at any point. Okay? So we have edge states now existing at all quasi-energies, even those quasi-energies that had bulk band overlapping with them before. And you could see this kind of in a numerical simulation here. We looked at different quasi-energies, and basically we looked at the green function for particles starting, say, in the corner here. And what you see is that if the particle starting in the corner here would always basically propagate along the edge, no matter kind of at which quasi-energy you look. While if you initialize the particle in the bulk, it will always kind of remain localized where you initialized it. Now, the fact that we have this edge state basically traversing the whole quasi-energy momentum zone leads also to this phenomenon of quantized pumping. Okay? So in this phenomenon of quantized pumping, we imagine the following thing. So we take this kind of cylinder or annulus, and we only fill it up with fermions, up until some distance from the edge. And I don't have to have a straight line. It could be any arbitrary line, basically so terminating this field region away from this other edge here. Okay, so I have kind of one region which is full here, which overlaps with this edge state here. Basically, since I have this edge state going across the whole momentum quasi-energy zone, what I'm going to see basically, if I look at the current, now you could imagine this state kind of carries the current because of this chiral edge state, and I can ask what is the current per period, and what you find is basically that the current per period is exactly quantized. If you kind of average over long times, the charge per period would basically asymptotically get to unity, okay, or any other integer which basically classifies this AFAI phase. And
sorry,
yeah.
The pumping is from.
No, the pumping is basically around the cylinder. Yeah. Mm-hmm.
Not from bottom to top?
No. So this is the point. So think about the bulk. The bulk is completely localized. So particles can actually not flow in this direction. The only delocalized states are here at the top and at the bottom. This is the reason why you get quantized pumping. If there were delocalized state across the cylinder, then basically particles could fly from one region to the other and basically spoil the quantization. But since the bulk is fully localized, then particles are, no matter how you initialize them, they always remain on this side of the cylinder and always overlap only with one right mover and not with the left mover. This is why you get a quantized pumping.
So the pumping is how much charge crosses?
Yeah, you can define a line here, say a cut across here, and you can ask how much charge goes across this every period. Yeah, and this is the thing that reaches unity.
Is it very different from Cohen-Hall effect?
Yeah, because I'm not looking at conductance here. I'm just asking at the current per time.
I understand, but suppose you take a Cohen-Hall on the cylinder and try to do exactly the same procedure. You don't have disorder. You just have
Right, but then again, in the quantum Hall, you have to connect to leads and you have to put a bias. You're not counting you're not pumping. You're not doing anything time dependent. You're not asking the question how much current or how much charge is transferred per unit time. That's not the question you ask.
I know, but I can ask the same.
Right. So in the quantum Hall in a quantum Hall system, I claim this would not be possible, because in a quantum Hall system, that's the main point. You always have. Maybe, I'm hoping this answers your question. So in the quantum Hall case, you always have the localized state going across the full sample. So in a quantum Hall, if this was a quantum Hall state, you would always have the possibility for particles basically flying across from the top edge of the cylinder to the bottom edge, and basically starting to flow in the other direction and spoiling the quantization. Okay? So this could not happen for a quantum Hall system. Yeah.
Can you cut the cylinder into two?
Right, and then you'd expose another edge state.
Why? They are localized. You just cut between.
No, but that's the point, that if you separate into two, you now you have two of these AFAI states.
But the
Okay.
information does not move from, one
No, but there's something when you cut, there's something very subtle going at the cut. Okay? So at the cut, you separate to a right and a left mover. We could talk about it more, but let me try to continue, then I could explain. And then one more interesting thing about this AFAI phase is that it actually, you could ask, okay, this is a fully localized state. Is it actually different? Is it really different from just an ordinary fully localized Anderson insulator? And the answer is yes. So here, what we did is we kept increasing the disorder, and then it's very strong disorder strength. So so this disorder strength is 40 times the hopping amplitude. You see that there is a phase transition. And in this phase transition, we find that really all the bulk states become delocalized now. And then on the other side of this transition, you just find an ordinary Anderson insulator. So you really have a phase transition between this anomalous Floquet Anderson insulator and just an ordinary Anderson insulator on this side. Okay, so now I've finished this first part. So again, if we go back to this question of steady states, so how is this related to the question of steady states? So the question would be, although this is not something we've chosen so far, the question would be, so this is a fully localized system, which is also topological. So you could now ask the question whether this system, even in the presence of interactions, would remain localized. and yet, for example, exhibit this quantized pumping. So suppose I add interactions here, the bulk is fully localized. Can I, for example, see this quantized pumping currents also in the interacting system? If yes, then this would be an example of a system which is interacting, closed, yet exhibits topological phenomena. Let me try to finish and then, okay?
We have 5 minutes.
5 minutes, that's 5 minutes less than I need, but okay. Okay, so the second part, which apparently is going to be short, I want to talk about a different system, and this is a system which is, it's again an interacting system, time-dependent, but this is, and it's going to be a one-dimensional system in this example, and this system in very long times, it's actually going to reach this, ultimate faith of being kind of fully random and kind of indefinite temperature-like state. But I'm going to claim that there is an interesting intermediate time behavior for this system. Okay, so what is the system? The system is just the Thouless pump. It's something that most of you probably heard about. Let me tell you, for those who don't know what it is, let me just tell you quickly. It's a one-dimensional system, okay? And there's basically two interesting parameters here. There is hopping, which is dimerized between the A and B lattice sites, so T and T prime. And we also have basically a sublattice potential. And if I basically now look in the plane of a staggered potential delta and this dimerization of the hopping, and I basically adiabatically go in a circle around the origin. I never go across the origin because the origin is a gapless point, so I go around the origin. Thouless claimed that for kind of non-interacting fermions, you're going to see basically a phenomena of basically quantized pumping. So one basically, or in this case, one particle would be pumped to the right every period. Okay, and this is again in the adiabatic limit. Okay, so what I want to do is I want to think about this Thouless pump in the language of Floquet spectra. And what we notice is that if I have a band, a 1D band that winds around the quasi-energy zone, this is related to the discussion before. If it winds, say, from -pi to pi, then if I fill up this band, it's going to give me a quantized current. Because basically the current or the charge flowing per period is just the integral of the E decay, and that's quantized for this type of dispersion. Okay? However, you cannot find this band structure in a one-dimensional system, even if in just a one-dimensional system, even if it's time-dependent. Okay? But I've showed you before that I could find this band structure on the edge of a two-dimensional system. But as a standalone one-dimensional system, this band structure is not possible. What's possible is to find this type of band structure, and this is the Floquet band structure of the Thouless pump. There is a right mover, there is a left mover, and there is an exponential splitting between them, which basically goes to 0 in the adiabatic limit.
I'm sorry, there's no chance you can do all 53 slides.
There's no, 30 of them are backup slides. So. I'll be done in a few minutes. Okay, so now how do we get basically a kind of an intermediate quasi-steady state which shows something interesting here? Again, the system is interacting, it's driven, it's going to go to the infinite temperature state. There's basically two types of scattering once we think about interactions that you have to think about. One of them is interband scattering, where I scatter particles, inside this right moving band, and there's also interband scattering between, say, the right moving band and the left moving band. Okay. Now, what I'm going to claim, maybe I'm going to skip the actual discussion, and you could ask me if you're interested. What I'm going to claim is that in the adiabatic limit, the interband scattering, those that take, say, a particle from the right moving band to the left moving band, are exponentially suppressed with respect to the intraband scattering. Okay? So the scattering that takes particles from the green to the yellow band are exponentially suppressed with respect to scattering within, say, this green band here. Okay? And I can explain why. Maybe I don't have time. But if I just want to explain what would happen if this would be true. Okay, so if this would be true, we could think about the following situation. We initialize some state. It could be a random state. We just choose momentum states here and occupy them randomly. But I only occupy particles in this green band. The current with this initial state is just arbitrary, okay? Because the dispersion doesn't have to be monotonic. So I could get any current, any initial current that I want. Okay, so arbitrary initial current. At intermediate times, actually very quickly, what happens is that particles start scattering within this green band. The intraband scattering within the band are actually very fast. And very quickly, I basically get an infinite temperature state, but only within the green band. Okay, so all the momentum states within the green band are basically occupied with the same probability, and any local correlator looks like I've calculated in an infinite temperature state, but it's a chiral infinite temperature state. Only in the infinite temperature state, only in terms of right movers. And if this is the case, then the total current would just be the density times the integral of the E decay, which is quantized. So the current would be basically the density times an integer, okay, over the period. Okay, so the charge transferred at each period is basically an integer times the density. And then at very long times, once the interband scattering starts kicking in, this current is going to decay. Okay, so this is exactly what we see when we look at kind of an exact. This is in exact numerics. We put the system. We use basically exact angulization to propagate the dynamics here. And you could see the following. So you start with some arbitrary current. This is the number of driving periods. And this initial current is just completely arbitrary. And once, very quickly, you see that this current decays to kind of something that looks flat. In fact, it's not flat, but it looks flat on this time scale. And this current is actually the density times this integer that we've discussed before. So this is our kind of quantized current in terms of the density. And then at very long times, you see this is 1,000 years, this is 40 years, at very long times, this decays exponentially. So all these intermediate regimes is kind of inside this part over here. And then you see this kind of interband scattering process kicking in and letting the current decay here. So this is exactly the type of behavior I've alluded to before. Okay, so this is my summary. So we've discussed two types of ways to get kind of topological states out of equilibrium. There's a third situation which considers coupling to external bath, and I'd be happy to talk about that with anyone that's interested. Thank you.
Okay, thank you.
Questions, comments?
Yes.
Anel, you mentioned earlier on the difference between a static system,
Yeah.
periodically, subject to Bloch theorem, and these Floquets. Now, imagine that you take a static system and put it on a torus,
Yeah.
subject to a flux inside. So you change the flux.
Yeah.
Adiabatically. Is it very different
From what? From
Floquet?
So the claim is that for Floquet systems, I could get states that are not possible in, for static Hamiltonian. And again, on a torus, what would I see? Okay, so on a torus, I could look at this. Right, so you're asking, if I look at on a torus, basically.
Static torus subject to.
Right, so on the torus, but I think what you're alluding to is the following thing. If you look at the static torus versus this driven torus, in both situations, you're not going to see edge states. So what's the difference between the quantum Hall? But in fact, you remember that I also had talked about this. Okay, so I also talked about this topological invariant that's a bulk topological invariant. Hold on a second. I'll find it. Here. Shift F. Okay, second. This thing here. Ooh. Okay, so there is this bulk topological invariant, okay, which is non-zero, okay, even for a system on a torus, okay. Now, this bulk topological invariant, you could ask, okay, so what kind of physical observable does it correspond to? So it turns out that if you look at magnetization currents, okay, in the bulk, you'll see a quantized magnetization current in the bulk. Okay, so this comes from this. If you look at this picture, okay, I claim that this is completely trivial, but you see that the particle actually does something non-trivial if you follow it throughout the period. So there's kind of orbital magnetization currents, and if you normalize them correctly, they are quantized. And this would not be present in the quantum Hall state.
But magnetization is in
Right, but again, so this is also kind of an equilibrium. It's kind of an equilibrium situation because I prepared. No, it's not an equilibrium, but it's a steady state situation, right? Because I prepared the particles in some states, and then I let the system evolve. But the system is fully localized, so it can't run very far away from what it started from, right? And then I could ask, okay, what is the magnetization currents? I need to average them over long times. But I can ask what are these magnetization currents, and if I average over long times, they're again quantized. And this is again, it's almost a steady state situation. There are small fluctuations because of, particles can jiggle a little bit around within their kind of localized state, but they can't go very far.
Okay, thank you, Netanel.